welcome to another module in this massive open online course. So, today or in this module let us start looking at a modulation scheme or a communication scheme which is known as amplitude modulation. Alright. So, let us start looking at amplitude modulation, which is an analog communication scheme and one of the earliest communication schemes developed and widely used. These principles continue to be used even today, that is amplitude modulation, often abbreviated as AM. Now, any communication system or communication scheme involves a carrier signal which is a sinusoidal signal. Alright. So, let us denote this carrier signal by CT, which is AC cosine 2 pi FCT. This is the amplitude of the carrier. And this is the carrier. So, FC is the carrier frequency, AC is the amplitude of the carrier, and this is basically your simply known as the carrier or the carrier wave. Alright. This is fundamental in every communication signal, a communication system, and the signal, that is the baseband signal or the message signal, is modulated on this carrier. Alright. There are various ways to modulate the carrier. One of the techniques is amplitude modulation, in which the amplitude of the carrier is modulated. So, in amplitude modulation, so what we have in AM is basically your amplitude of the carrier, that is message modulates the amplitude of the carrier, and an AM signal is given as, the AM signal is described as xt, which is equal to 1 plus Ka. Let me write the expression 1 plus Ka mt times the carrier, that is AC cosine 2 pi FCT, which is also basically AC plus 1 plus Ka times mt into cosine 2 pi FCT. This is the standard form or the canonical form of the amplitude modulator. So, this is your amplitude modulated. This is the amplitude modulated signal. All right. And let us explain. Of course, we have already seen what is AC. AC is the carrier amplitude, FC is the carrier frequency, Ka, this constant Ka is also known as the sensitivity. Ka is the sensitivity. The sensitivity of this AM signal. Of course, MT is this is the message to be transmitted. This is your message signal, that is the message we want to communicate or the message that we would like to transmit. All right. Now, if you see what is happening in amplitude modulation is we have a carrier all right, cosine 2 pi fct. Now, when we multiply this carrier by the message, right, now the amplitude of the carrier, the unmodulated carrier AC cosine 2 pi fct, which is constant, that is the amplitude of the unmodulated carrier is simply AC. Now, once you multiply the message, that is 1 plus Ka times mt, the amplitude of this carrier varies according to the message, all right. So, this is basically the amplitude of the carrier is modulated, right. When the amplitude of the carrier varies according to the message, another way to say this same phenomenon is that the amplitude of the carrier is modulated by the message. Therefore, this is also known as amplitude modulation, all right. So, what we have here is basically to explain this thing, the amplitude of the carrier. You can see that the amplitude of the carrier is varied or modulated according to the message So, we have the modulate. So, modulation is nothing but the variation. So, what we have when we multiply the message by, when we multiply the carrier signal by the message, the amplitude, one can think of it as if the amplitude of this carrier signal is being modulated by the message. Therefore, this is termed as amplitude modulation. So, the amplitude of the carrier, which was previously constant, is now time varying in nature, and it varies as per the message mt. All right. So, to understand this, let us look at a simple example. Right. Let us consider a simple example. Let us describe this by a picture. So, I have, let us consider AC, that is amplitude of the carrier to be 1. Remember, Ka is the sensitivity. Let us choose K equal to half and FM, the message frequency is equal to half. Let us choose the message to be a pure sinusoid, mt equals cosine to pi fmt, fm equal to half. So, this is simply cosine of pi t, this is your message signal. Therefore, the AM signal x t equals x t is given as AC, that is 1 into 1 plus Ka, that is half cosine pi t times cosine 2 pi fct. This is your amplitude modulated signal. All right, we have chosen the sensitivity K equals half. We have chosen the message to be a pure sinusoid, that is cosine 2 pi fmt with fm equal to half. So, it is cosine pi t. So, the amplitude modulated signal is 1 plus half cosine pi t times cosine 2 pi fct, where we have chosen the carrier amplitude AC also to be equal to unity. Now, if we plot this, this will look something like this. Let me first draw the time axis, correct. Okay, and now if you look at this 1 plus half cosine pi t, the maximum value of this is basically 3 by 2 when cosine pi t equals 1, and the minimum value of this will be the minimum value of 1 plus half cosine pi t will be half when cosine pi t is minus 1. So, this varies between this varies between half and 1.5, that is 3/2. So, I have over here 1, let us say I have over here 2, and this is half, this is 3/2. So, now for instance, when t equal to 0, I have 1 plus half cosine pi t equals 1.5, that is 3/2, and at t equal to 0, this is equal to 3/2. At t equal to 1 plus half cosine pi t is 1 minus half, that is half. So, at t equal to 1 it is half, and once again at t equal to 2, this is going to be equal to 1.5. At t equal to 3, this is going to be equal to half, and so on. So, if I join these points now, I have some signal that looks like this. Right? I have some signal that looks like this. Now, let us reflect this, let us construct its mirror image about the origin. So, the mirror image about the origin will look something like this. So, there is 3/2, it's minus half. So, the mirror image will be between minus 3/2 and minus half, and that is going to be something like this. That is basically reflection of this about this. So, I have this. Now, the carrier, the modulate the carrier, basically the amplitude of the carrier is changed is varied according to this. So, I have a carrier whose amplitude varies according to this, the modulating signal. So, I am going to have something that looks like this, correct. So, what is this? This is basically your cosine 2 pi FCT, this is the carrier, this is 1 plus half cosine pi t, this is the modulating signal. Now, if you look at this, the carrier, correct, the carrier, basically the amplitude of the carrier is modulated by the message signal. Therefore, if you look at the peaks of the carrier basically trace the message signal, the peaks of the carrier. So, the curve that is traced by the peaks of this carrier, that is termed as the envelope of the carrier, and that is very important because that contains the information. So, if you look at the peaks, if I sample this at the peaks, right, the peaks follow the message signal. So, this is termed as the envelope, and that is an important aspect. This is termed as the envelope of the carrier, and this contains the envelope of the carrier. This contains, so we have the amplitude of the carrier which is modulated the amplitude of the carrier is modulated by the message. Therefore, envelope of the carrier contains information therefore, envelope of the carrier contains the information about the envelope of the carrier contains the information about the message signal. And further if you look at this we have implicitly assumed, and this is true of all communication system, that the carrier frequency is much larger. For this amplitude modulation or for any communication system to work, we need the carrier frequency to be much larger than the message frequency. Alright. So, the carrier frequency Fc is typically much larger than the message frequency Fm. Alright. So, carrier frequency so Fc is much greater than Fm, correct. Fc is your carrier frequency. Of course, we are considering a pure sinusoid. So, Fm is the message frequency, otherwise you can also think of Fm as the maximum frequency of the message, maximum frequency component in the message, that is the message is band limited between message is band limited between -Fm to Fm. Therefore, the maximum frequency component of this message signal has to be much smaller than the carrier frequency. The carrier frequency usually chosen is much larger than the maximum frequency component of the message frequency. Alright. So, you can see that the carrier frequency is much larger than the message frequency. Now, another important implicit assumption here is the following thing. Let us, which we will understood, let us consider another example by choosing the same system when we choose Ka equals 3/2, that is a higher, previously Ka equals half, that is we are choosing a higher sensitivity factor. Now, if you look at 1 plus Ka times empty, 1 plus Ka times empty equals 1 plus 3/2 cosine pi t, the maximum of this is 5/2 and the minimum of this is minus half. When cosine pi t is -1, this is 1 minus 3/2, which is minus half. Now, if you plot the same thing, that is the signal that is modulated by this. So, I have 1, 2, 5/2. So, this lies between minus half to this lies between minus half to minus half to 5/2. So, this is let us say your 5/2 and this is let us say minus half. Again the same thing, this is point, this is 1, 2, that is time 1, time 2, time 3 and so on. At time t equal to 0, this is equal to 5/2. At time t equal to 1, this is equal to minus half, correct. At t equal to 1 this is cosine pi. So, 1 minus 3 by 2 is minus half. At time t equal to 2 again this will be 5 by 2, and time t equal to 3 this will be minus half. And if I now join these points, what I will get is something that looks like this. Right, and of course, if I can draw the mirror image of this again, the mirror image will be between minus 5 by 2 and half. So, this will be 5 by 2 half, 5 by 2 half. So, the mirror image will be something like this. And now, if I draw, so this is basically your envelope, and now if I draw again the carrier which is modulated by this, the carrier which is modulated by this message signal, I have something like this. And this, if you can look at this again, if you can look at this, you can see something very interesting. At this point, 1 plus k times mt equals 1 plus 3 by 2 times cosine pi t, all right, starts equal to 0, and at this point it starts going negative. So, there is, so at this point at t equal to, if you look at this point at t equal to 1, at t equal to at this point, correct. So, at this point it basically starts to go negative, correct. So, this is your point 1. So, at this point it starts to go negative, that is message 1 plus k m t starts becoming negative, correct. So, the envelope starts to become negative. So, there is a phase reversal. So, there is a phase reversal in the envelope, correct. There is a phase reversal in the modulating signal, there is a phase reversal and therefore, what you can see, if you track the envelope of this, the envelope is going to be this, correct. So, there is going to be, instead of tracking the correct envelope, you are going to track a distorted version of the envelope. So, this leads to envelope distortion. So, what is happening is because since 1 plus k m t is negative, correct, and when you track the envelope, you continue to track the positive envelope, and what happens eventually is that you will encounter is that you will have, this leads to envelope distortion. So, if 1 plus, so if Ka is much large, all right, if Ka is much large, that 1 plus k m t, right, can take negative values, that leads to phase reversals of the carrier, correct, that leads to phase reversals, and this leads to envelope distortion when you track the envelope of the carrier, alright. So, eventually this was the true envelope, right, this was, so the true envelope. So, to draw this again over here, the true envelope is this is your true envelope, and what you end up tracking, but what you end up tracking is something that is like this. This is your tracked envelope, and this leads to envelope distortion. And this leads to envelope distortion, therefore, because it undergoes a phase reversal, correct. And therefore, to avoid envelope distortion, we can clearly see that the sensitivity factor Ka should be chosen appropriately to avoid envelope distortion. Choose the sensitivity factor K appropriately. In particular, one must have 1 plus Ka Mt to be greater than or equal to 0, alright. This is the condition, correct. The envelope has to be greater than or equal to 0. This is the condition for no distortion. Which means, and this implies that Ka times the magnitude of the minimum of Mt, Ka times the magnitude of the minimum, that is when Mt goes negative, the magnitude of this minimum, Ka times the magnitude of this minimum must be less than or equal to 1. That is what we are saying is, when Mt becomes negative, if you look at the magnitude of that, Ka times the magnitude of this trough, Ka times the magnitude of this lowest point of Mt or this negative peak of Mt must be less than or equal to 1 for no envelope distortion, alright. This must hold for no envelope. This condition must hold for no envelope distortion, and this constant Ka times magnitude of Mt, this is known as mu, the modulation this is known as mu, that is the modulation index, alright. The modulation index of this amplitude modulated system, mu equals Ka times the magnitude of minimum of Mt, where mu is the modulation index of this amplitude modulated system. Now, for no distortion, so for no envelope distortion, mu is less than or equal to 1, correct. Mu has to be less than or equal to 1 for no distortion. if mu is greater than or equal to 1, if mu is greater than 1, then the carrier is said to be, then there is going to be envelope distortion, the carrier is said to be over modulated. So, over modulation of the carrier leads to envelope distortion. So, if mu is greater than 1, this is basically over modulation. Carrier is when mu is greater than 1, then carrier is said to be over modulated, and over modulation leads to envelope distortion. Alright. So, if the carrier is over, for instance, in our two examples here, correct. Now, look at this, our MT is cosine pi t, all right. Therefore, minimum magnitude MT, magnitude of minimum MT is basically your modulus minimum of MT cosine pi t is -1, magnitude of -1 equals 1. Therefore, mu equals Ka times 1 equals Ka, which is equal to Ka is, for this case K equals half. So, this is equal to half, which is less than 1. So, therefore, there is going to be no envelope distortion, implies this implies no distortion, correct. However, here let us, if you look at the second example, Ka, in this case we have Ka equals 3 by 2 Ka times magnitude of minimum of MT equals 3 by 2 into 1 equals 3 by 2. So, this is basically your modulation index is greater than 1, therefore, this is over modulated. So, this is basically over modulated, since the modulation index mu is greater than 1. Alright. So, we have seen two scenarios with a message signal cosine pi t, when k maximum value, that is the magnitude of minimum MT is 1. So, when Ka equals half, this is under modulation, this is normal, there is no distortion, alright. However, when K equals 3 by 2, this signal, the modulation index mu is Ka times 1, that is 3 over 2, which is greater than 1, alright. So, this the resulting carrier signal is the resulting modulated signal, the resulting carrier is over modulated, and that leads to envelope distortion, that leads to phase reversals and envelope distortion. Okay. And finally, for a sinusoidal message signal, correct, we have MT equals AM times cosine 2 pi FMT. This is amplitude of your message, this is the message frequency, correct. this is the message frequency, and you can see magnitude minimum mt, the minimum value of am cosine 2 pi fmt is minus am. So, magnitude minimum mt, if am is positive, that is magnitude minimum am, which is am, correct, implies mu equals Ka times am, correct, mu equals Ka times am, which means the modulation index equals the sensitivity times the amplitude, sensitivity times the amplitude for a sinusoidal message signal. However, it is important to remember this is only for a sinusoidal message signal MT. Alright. So, the modulation index mu equals the sensitivity Ka times the amplitude A. Alright. So, in this module we have started, alright, we have started looking at amplitude modulation, which is one of the most fundamental, I would like to say, one of the most fundamental and one of the earliest schemes of transmitting, that is transmitting and receiving communication signals, or basically one of the amplitude modulation forms one of the earliest technologies of communication. Alright. So, we have looked at amplitude modulation, that the structure of an amplitude modulated signal, correct, examples of amplitude modulation, also the concept of the envelope of an amplitude modulated signal, and also when is there and what is the envelope, when is there no envelope distortion, and also when is the carrier or the condition for over modulation of the carrier, and the condition, alright, the condition for no, and when there is no envelope distortion, and the condition when the carrier is over modulated, which leads to envelope distortion. Alright. So, we will stop here and look at other aspects in the subsequent modules.